See, we are entering into the third section of the Neet 2025 chemistry question paper discussion. Here the first question, 58th question, it is from coordination chemistry. This question is about the ionic conductances of various complexes. See, the question here is that out of these four complexes, which will be having more conductance? And the first complex is CONS3 5 times Cl, 1 Cl outside. Means it is a +1 ± type ion. One cation and one anion it is producing, both with one charge. Next one, CONS3 tri-Cl3. It is a non-ionic type. 0 ions are produced. Third is CONS3 4 times Cl2. It is another non-ionic case. 0 ions are produced. And finally we have CONS3 6 times Cl3. Means it produces one cation with the 3 plus charges and 3 anions with the 1 minus charge each. If the question were which is having the highest conductance, it would definitely be 4. But here the question is that which is having the lowest conductance. Here, as such, these two will have no conductance because both of them are non-ionic. In that case, it must be an error to include both. Then this question would get cancelled. If they were included deliberately, the questions with another notion that even complexes can have this coordinate non-ionic species can have dissociation. In that case, this will be slightly more conducting than this because if at all it dissociated, it would produce CO3 plus and Cl minus 3 Cl minus. Whereas this would produce CO2 plus and 2 Cl minus. If at all the complex part dissociate to slight extent. Okay. In that case, this third case will be the case having the lowest conductance. So, regarding this question, there are two possibilities. One is the cancellation of the question. The other is, if at all it is an accepted question, 3 will be the answer because it will be producing less number of, it will have a less degree of dissociation of the complex ion, producing less number of ions and a low conductance. Okay. So, either cancellation or option 3 will be the answer. Okay. Now question number 59. This is again from hydrocarbons. See, the question is this. Which among the following will not give benzene as the product? Which negative type of question. Which of the following will not give benzene as the product? We will check. This is the first reaction. Disonium chloride warmed with the water. We know when disonium chloride is warmed with the water, disonium group is replaced by OH group and not by H. So we get phenol here, not benzene. So we expect the first itself to be the answer. Anyhow, we will check the remaining cases. Also. The second case, soda lime distillation of a sodium benzoate. That's a popular method to prepare an alkane or arene, RCOO minus Na plus, or pH benzene ring, COO minus Na plus, both when distilled with soda lime. Soda lime mixture is calcium oxide plus NaOH. What will happen? CO2 group will be removed and you will get a benzene as the product, no? You get benzene plus Na2CO3. Isn't it? So, soda lime distillation, NaOH plus CaO. That is soda lime. So, you get a benzene as the product in that case. And third case they have mentioned hexane. Upon heating with the molybdenum oxide MO2O3 at 773 Kelvin and 10 to 20 atm pressure, that will lead to reformation, cyclization followed by elimination of 3 pairs of hydrogen, giving you benzene. Totally 4 pairs of hydrogen will be removed. One for the cyclization process. From the terminal carbon, a pair of hydrogen will be removed. So it will first become cyclohexane. Then 3 more pairs of hydrogen will be removed to make alternate double bonds. So a total 4 pairs of hydrogen will be removed to give you benzene. So that's also a case where benzene is a product. So the last one we have studied in hydrocarbon, aromatic hydrocarbon in first year, that when acetylene is passed through a red hot iron or copper tube, they cyclically trimerize to produce benzene. Cyclic trimerization produces benzene. So in all these 3 cases, other than the first case, benzene is the product, and for this question, answer will be doubtless 1 will be the answer. Okay. The next question is from again coordination chemistry, and here we have to identify among the 5 given complexes which are paramagnetic, that is, which are having unpaired electron. So such question always involve detailed checking. If you are provided with the complexes which in your syllabus already studied in detail, then it will be easier for you. Otherwise, if a new one is given, you have to study that and check whether there is unpaired electron or not. But here, luckily, 3 complexes are familiar to you, yet we will explain. The first one is NaCl4 2- nickel complex with 2 plus charges for nickel, because Cl minus 4. Even then 2 minus is remaining, means nickel is 2 plus. So first we write nickel's valence electronic configuration 4s2 3d8. 4s2 3d8. You must be familiar with that. So presently it has 2 unpaired electron in the d subshell. Okay. Now it has to undergo oxidation and become Ni2 plus by releasing 2 electron. That release takes place from 4s orbital. So we have Ni2 plus 4s0 3d8. 3d8 electron remain as such. Since chloride is a comparatively weak ligand, it does not change the or pair up the unpaired electrons in the d subshell. Being unable to do so, it makes use of this vacant s orbital and 4s orbital and 3 vacant 4p orbital to undergo sp3 hybridization and to produce this tetrahedral complex with the 2 unpaired electrons retained. So NaCl4 2- is paramagnetic tetrahedral sp3 hybridized. Okay, so that is very much from our textbook with the explanation. The next one, NaCO4. That's also from our textbook with the detail. Again, we since all are Na cases, it is very easy, comparatively easy for us to learn. You don't have to, even though on the board I have written the same thing repeated all the time. In the actual process, you don't have to, because you know what is Na. Na with the 2 unpaired electron. Here it is a neutral complex, so no electron removal, but carbonyl group being the most strong ligand can rearrange and produce vacancy within the 3d orbital. These 2 unpaired electron will get paired up in the d orbital. Okay. So it has a vacant d orbital in the excited state. But s orbital is still unavailable for hybridization. So what will happen? In the 3rd stage, this paired electron will be shifted to d orbital, creating vacancy in the s orbital. So like this, now this also undergo sp3 hybridization, producing a tetrahedral complex of NaCO4. So this and this both involve same hybridization, similar structure, sp3 tetrahedral. But the difference is that it is paramagnetic due to the presence of two unpaired electrons, whereas it is diamagnetic due to no unpaired electron. So this is paramagnetic, this is diamagnetic. The third is NaCN4 2-. Three complexes in a row from the textbook, where also they are discussed in a row. Okay, NaCN4 2-. First Na become Na2 plus, S become vacant, Cn is a strong ligand, so it pair up these two electrons. So it has vacant s orbital, vacant d orbital, and also vacant p orbital. It undergoes dsp2 hybridization, 3d, 4s, 2, 4p. dsp2 hybridization and form square planar complex. Square planar complex. Here also there is no unpaired electron, and so this is diamagnetic. Next is NaH2O 6 times 2 plus. In NaH2O 6 times 2 plus, Na is again 2 plus. So nickel, 2 electrons removed from s orbital. Being very weak ligand, it cannot pair up the electron. So to make sp3d2 hybridization, it makes use of this s orbital. Next d orbital, next set of d orbital, and I mean 4s, 3, 4, out of this 4p, all the 3 are used, and 2 vacant d orbital from the outer 4d. So it will be forming an outer complex, isn't it? Because it is making use of the outermost available vacant d orbital. Inner d cannot be used because it is either filled or half filled with electron. Further, H2 is a weak ligand, and so it cannot pair up electron and create vacancy within the inner 3d. So it make use of s, p and d orbital, all the 3 of the outer subshell. So it forms an outer complex by undergoing sp3d2 hybridization. Okay, so this will be producing another paramagnetic complex. Finally, you have one molecule that is out from the textbook, normally not explained, but PPS3, here NAPPS3, triphenyl phosphine is the ligand. It is a moderately strong ligand. Okay, NAPPH3, PH stands for phenyl benzene ring. So a phosphorus atom to which 3 benzene rings are connected. That is triphenyl phosphine. 4 such triphenyl phosphines are attached to the central nickel in the neutral state. So since it is a strong ligand, its characteristic will be similar to NaCO4. Means Na ground state, pair up, one pair from S to D transfer, create vacancy in S, and making use of S and 3p, sp3 hybridization. So we have again a tetrahedral complex, NaCO4 and NAPPS3 4 times, will be similar in aspects like hybridization, structure, and in diamagnetism. So far in our study we found that this is para, this is dia, this is dia, this is para, this is dia. A and D are the cases with the unpaired electron, and so paramagnetism. So A comma D, 4 is our answer for this question. Okay. Okay. Question number 61. It is from hydrocarbon. Look, the question is, among these 4, which will not decolorize bromine water? Which will not decolorize bromine water? See, this is aniline. We know that aniline, in aniline, amino group is an activating group. And so, when treated with the bromine water, what will happen? It will undergo orthopara bromination. Br, Br, Br plus 3HBr. This reaction will occur. And so the added bromines, reddish brown color will disappear. This will be a white precipitate. So bromine water decolorizes what? Aniline. Now cyclohexane. The bromine water cannot do anything, no. So that will be our answer. Next is phenol. Phenol, we have similar to aniline. Both OH and NH2 are activating group. So substitution, not addition, substitution with the bromine. Again, a white precipitate will be formed there also, like the case of aniline. A tribromophenol, 2,4,6 tribromophenol will be formed. So added bromine water will be discharged in its color. And lastly, we have what? Styrene, ethynyl benzene, isn't it? Styrene. The addition happens, not substitution. In the double bond, bromine will be added across. So there also what happened? The added bromine's color will be discharged. So for this question, nobody will go wrong in this question, I suppose. 2 will be our answer. Okay, 2 is the answer. Our next question, its reactions are from different chapters, so you cannot pinpoint to which chapter it belongs. See, you have to identify the name of the reaction versus its corresponding catalyst. Okay. See, first one is Haber process. We know ammonia manufacture from nitrogen and hydrogen. You use iron as the catalyst. Okay. So, Haber process, iron catalyst, that they combine. Then Walker process, it is the method to convert an alkene to an aldehyde or ketone. Look here, CH2 double bond CH2 plus PdCl2 plus H2O in the presence of CuCl2 and O2. Alkene plus PdCl2 plus H2O in the presence of cupric chloride, CuCl2 and oxygen. You get CH3CHO plus PD plus 2HCl. That reaction is called a Walker process. So we can say here PdCl2 is used. Here it is not, you cannot strictly say it is a catalyst because it is converted to PD. But in a cyclic process it is get converted back to PdCl2. So that way you can say in the cyclic process it is used as a catalyst. So Walker process involves PdCl2. Wilkinson's catalyst. It is a hydrogenation catalyst. Wilkinson catalyst, what is it? It is a complex. It is tris triphenyl phosphine rhodium 1 chloride, PPS3 thrice. Triphenyl phosphine, PPS3 thrice. Tris, such 3 molecule with the rhodium chloride. It is called Wilkinson's catalyst. It has the advantage that it is soluble in organic solvents, and so you can hydrogenate in a homogeneous solution, unlike solid catalyst where only on the surface hydrogenation can happen between two, for example ethene plus hydrogen giving ethane. That can happen only on the surface of platinum, palladium, etc. But here this catalyst being soluble in the organic solvent, it will be more easier. Every molecule can catalyze, but in the other case only surface molecule can catalyze the reaction. So it will be more efficient, Wilkinson's catalyst. So its catalyst is PPS3 thrice RHCl. Okay. And Zigwanata catalyst is a familiar another hydrogenation catalyst, isn't it? We know titanium tetrachloride plus aluminium, either trichloride or in this case aluminium trimethyl is taken. Okay, so we'll get here the given order itself is the correct answer too. Means A1, B2, C3, D4. 4 is the answer. There is no shuffling required. As such, the answers are. Okay, hope you followed that. Next is from biochemistry, the question number 63. See, you have to match the vitamin with the corresponding deficiency problem. Okay. B12, we know cyanocobalamin. One of its deficiency issue is pernicious anemia, isn't it? Okay. Then D, vitamin D, sunshine vitamin, calciferol, rickets, deforming of the bones. Then B2, riboflavin. What is its deficiency problem? Chelosis, that is the fissuring, cracking at the mouth's corners. And B6, pyridoxine, convulsion, uncontrolled movement of muscles and related pains, convulsion, B6, pyridoxine. So B12, pernicious anemia, D, calciferol, rickets, B2, riboflavin, chelosis, B6, pyridoxine, convulsion. This is the correct matching. 4, 3, 1, 2. 4, 3, 1, 2. And that corresponds to given in among the given set. 3 is the answer. Okay. Okay. The next question. You can say it is from DNF block elements. Okay. It is regarding the number of unpaired electron in 2 species. See, it is statement type question. Statement 1. Ferromagnetism is an extreme case of paramagnetism. Yeah, because paramagnetism arises when there are few unpaired electrons. Agreed. Whereas ferromagnetism is involved when there is large number of unpaired electrons in an atom or ion. So that is correct. Ferromagnetism is an extreme case of paramagnetism. The next statement given is Cr2 plus and Nd3 plus are having the same number of unpaired electrons. They have also given the atomic numbers of chromium and neodymium, Nd. So you have to write, if you don't know by heart the electronic configuration, you have to write it and find it out. Okay, that's the only problem. See, chromium we know from our familiarity. Chromium is having in the ground state 6 unpaired electron, 4s1, 3d5. So if you remove 2 electron, one will be removed from here and the other will be removed from one of the T subshell. So it will be having 4 unpaired electrons. Cr2 plus will have 4 unpaired electrons. What about Nd3 plus, neodymium 3 plus? 2 will be removed from here and 1 will be removed from one of the F subshell. So there will be 3 unpaired electrons here. So second statement is incorrect because they are not having the same number of unpaired electrons. So first statement correct, second statement incorrect. That is option 4 is the answer for this question. Okay. See the 65th question. T half is 1 minute. Then what is T 99.9%? That's the question. So it is from chemical kinetics, doubtless. See, to answer this, you must know what is the fractional life of a first order reaction. Ty by x is equal to 2.303 by k log x divided by x minus y. You make that form by heart. Then you apply it for T and now we take ratio of these two. T 99.9% by T half. See in the ratio 2.303 for both cancel. Then we have to write only log x divided by x minus y, isn't it? Log x divided by x minus y alone we need write. Log here 99.9 by 100. So x is 100 by x minus y. 100 minus 99.9 is equal to 0.1 divided by log 2 divided by 2 minus 1, 1, isn't it? Yeah, is equal to log 1000 by log 2 is equal to log 1000 is 3, log 2 is 0.3010, we can approximate it to be 0.3. So 9.9 approximated to 10. Here one of the answer is 10. That's why I have approximated that to 10. And so our answer for the question number 65 is 1, which suggests 10 minutes. Okay? Take care.